Every application you have ever used stores data somewhere. And behind the scenes, every engineering team faces the same fundamental question early in the build. Do we use a relational database or a NoSQL one? Get it wrong and you are rewriting core infrastructure 6 months later under pressure, with users already depending on it. Get it right and your system scales gracefully as the product grows. The frustrating part is that both choices are correct in different situations. SQL and NoSQL are not competing answers to the same problem. They are different tools built for different shapes of data and different access patterns. This video is going to give you a clear mental model for telling them apart, understanding what each one does exceptionally well, and knowing which one to reach for when you sit down to design a system from scratch. No vague rules of thumb, actual engineering reasoning you can apply immediately. At the highest level, the split is about philosophy. SQL databases, also called relational databases, are schema first. Before you can insert a single row, you declare exactly what columns exist, what types they hold, and what constraints apply. The database enforces that contract on every single write. NoSQL databases flip this around entirely. They are data first. You store whatever shape you have right now, and your application code handles structure at read time. This is called schema on read. Neither approach is obviously better than the other. Strict schemas catch errors at write time and make data trustworthy across the entire organization. Flexible schemas let your product iterate quickly without expensive downtime migrations. About 40% of production databases today are still relational SQL. About 60% of new projects in 2024 include at least one NoSQL store. And many mature systems use both simultaneously, a pattern called polyglot persistence. The relational model was invented in 1970 by Edgar Codd, and it is genuinely elegant decades later. Data lives in tables. Tables have rows. Rows share a fixed set of typed columns. When two tables have a relationship between them, you express it through foreign keys and query both together using a join operation. This lets you ask arbitrary questions about your data at any time, including questions you never anticipated when you first designed the schema. The SQL query language makes this enormously expressive. Select, join, group by, window functions, and aggregate operations. A single query can span multiple tables and return precisely the data you need. Backing all of this is the ACID guarantee. Atomicity means a transaction either fully completes or fully rolls back, never leaving partial state. Consistency means every write leaves the database in a valid state matching your declared rules. Isolation means concurrent transactions do not corrupt each other even under heavy load. Durability means committed data survives crashes. Popular SQL databases include PostgreSQL, MySQL, SQLite, Oracle, and SQL Server. NoSQL is not one thing. It is a family of 4 quite distinct database types, each optimized for a specific access pattern. Document databases like MongoDB and Firestore store data as JSON-like objects called documents. Each document can have a completely different set of fields, making them excellent for content with variable structure like product catalogs or user profiles. Key value stores like Redis and DynamoDB are the simplest possible model. Every piece of data has a key, you retrieve it by that key, and you get the value back in microseconds. Perfect for caches, sessions, and rate limiting at high volume. Wide column databases like Cassandra are arranged in rows where each row can have a different set of columns. They are built for massive write throughput, handling billions of events per day across hundreds of distributed nodes. And graph databases like Neo4j model data as nodes connected by edges, with each relationship being a first-class citizen in the data model. If your core problem involves traversing relationships at depth, who follows whom, what is recommended based on purchase history, graph databases make those queries natural and fast. The schema difference has real and concrete engineering consequences. When you use SQL, adding a new field to a table requires a migration. Run alter table, which on a table with hundreds of millions of rows can take minutes or hours and may block writes during execution. You plan these migrations carefully, often using zero downtime strategies involving multiple coordinated deployment steps. The payoff is that your database enforces data integrity on every write. Invalid or malformed data simply cannot enter. With NoSQL, adding a field to a document is trivially easy. You start including it in new writes. Old documents do not have the field, new ones do, and your application code handles the difference at read time. This makes product iteration genuinely fast. The cost is that the database will not stop you from writing inconsistent or malformed data. That enforcement responsibility moves entirely into your application layer. The right choice depends on how stable your data model is expected to be and how much trust you place in your application to maintain invariance the database is not enforcing for you. Both SQL and NoSQL can scale, but they do it very differently, and the difference matters significantly at high traffic volumes. SQL databases traditionally scale vertically. You provision a bigger server with more RAM, faster CPUs, and higher throughput storage attached to a single powerful machine. This approach is simple to reason about because there is one database. ACID transactions work naturally across all data, and you never have to think about data distribution or network partitions. The practical ceiling for a well-tuned PostgreSQL instance is around 10 terabytes before cost and hardware limits become serious constraints. NoSQL databases are designed to scale horizontally from the ground up. You add more nodes to a cluster, and the database distributes your data across them automatically through a process called sharding. A Cassandra cluster can hold hundreds of terabytes on commodity hardware with linear write scaling. This flexibility comes from a fundamental constraint described by the CAP theorem. Any distributed database can only guarantee two of three properties simultaneously: consistency, availability, and partition tolerance. SQL databases typically prioritize consistency. Most NoSQL databases prioritize availability, meaning they may return slightly stale data during a network partition. The query model is where SQL genuinely shines and where NoSQL imposes the most upfront discipline on your thinking. SQL lets you query any column, join any set of tables together, and aggregate data in ways you never anticipated at design time. You can add an index to any column at any time, and the database will use it automatically across all existing queries. This flexibility is enormously valuable for analytics work, operational reporting, and exploratory data investigation. NoSQL databases require you to think carefully about your queries before you design your schema. You identify the specific access patterns your application needs, then you model your data to serve those patterns efficiently and directly. A MongoDB collection query not covered by an index performs a full collection scan, reading every single document in the collection. A Cassandra query not aligned with your partition key simply does not work at scale. This upfront discipline pays off at read time with extremely fast, predictable, and consistent performance. The trade-off is rigidity. Queries outside your original design are painfully slow or outright impossible without a schema overhaul and full reindex. Choosing between SQL and NoSQL becomes much more straightforward once you know your access patterns clearly. E-commerce backends need SQL. Products, users, orders, and inventory are all deeply related, and you need flexible cross-table queries you cannot predict ahead of time. Session stores need NoSQL, specifically Redis or DynamoDB, because you are doing millions of sub-millisecond key-value lookups with automatic expiry. Social graphs need a graph database like Neo4j because friend-of-a-friend queries at arbitrary depth are first-class native operations. Real-time event analytics need a wide-column store like Cassandra or ClickHouse because you are writing billions of events and reading them back in aggregated dashboards. Content management systems with variable page structures are a natural fit for document databases like MongoDB. Financial transaction systems need SQL because ACID guarantees are simply non-negotiable. Full-text search belongs in a specialized engine like Elasticsearch or Typesense. Machine learning feature stores often span both, with a SQL database for structured training data and a fast key-value cache for inference-time lookups. In practice, almost no mature production system uses just one type of database. The industry pattern is called polyglot persistence, and the principle is straightforward. Each database type gets used exclusively for what it does best. Your application writes authoritative state to PostgreSQL because ACID guarantees matter for every order, payment, and inventory update. High-traffic read paths route through a Redis cache layer so product pages load in milliseconds regardless of concurrent user count. Search is powered by Elasticsearch, kept in sync via change data capture streaming from the primary PostgreSQL instance. Analytics run against a ClickHouse column store where billion-row aggregations complete in seconds rather than hours. Uber does this with PostgreSQL for trip data, Cassandra for raw location history, and Redis for surge pricing calculations. Airbnb uses MySQL for listings and bookings, Elasticsearch for search, and Redis for user session. Twitter built MySQL for tweet storage alongside a custom graph store for its social graph traversals. The pattern is consistent across all of them: one trusted write store for system of record data and many specialized read stores serving specific query shapes. So here is the decision framework distilled to one sentence. Use SQL when your data has stable relationships between entities and you need the freedom to query it flexibly. Use NoSQL when you have a specific high-volume access pattern and you are willing to model your schema explicitly around that pattern. And in any system that has grown beyond a simple single-page CRUD application, you will almost certainly end up using both in some combination. Understanding the trade-offs rather than following rules gives you the judgment to make that call correctly for each part of your system. If this gave you a clearer mental model of the database landscape, subscribe because we cover systems design, algorithms, and how real production infrastructure actually works. Thanks for watching.